In this video, we'll continue our discussion of section 3.1 with another application. This will be an in-out rate with mixing two fluids. So the mixing of two fluids sometimes gives rise to a linear first order diffie. The rate A prime at which the amount of salt in the mixing tank changes, the way it changes is a net rate. So this rate, and remember A in this case is going to be the amount of whatever substance. In this case, in a minute, we're going to talk about salt. So I'm just going to say salt. But this would be the input of the substance if you want to change that, or the output minus the output. So this makes sense. If I have this much salt coming in and this much salt going out, the amount container inside the container would be the difference of the two, right? If I'm pumping 10 out, 3 out, I would have 7 in there, right? So, okay, so we have R in, R out. These are going to be a little weird. I know in the book, this problem, I think this problem's in the book, but I know when I was reading it and I saw this problem in the past, there's one little part that they don't explain well at all. So I figured I would just do this problem, and it really models all the others. Okay, so a large tank holds 300 gallons of brine solution, that's salt and water. Salt is entering and leaving the tank. A brine solution is being pumped into the tank at a rate of 3 gallons per minute. It mixes with the solution there. And then the mixture is pumped out at a rate of 3 gallons per minute. The concentration of the salt in the inflow or solution entering was 2 pounds per gallon. So they're entering salt. If 50 pounds of salt were dissolved initially in the 300 gallons, how much salt is in the tank after a long time? Okay, before we start answering A and B, we're going to go ahead and create our diffie by figuring out what R in and R out is. Okay, so how we set this up, remember R in is the amount of salt. So beginning, if we look, okay, I know the amount of water that's going in, the solution, a brine solution is 3, and I'm going to write it like this to help me, 3 gallons per minute. Okay, and then I know that in that 3 gallons, we were putting 2 pounds of salt in that brine solution. So I got 2 pounds per gallon. Now notice if I were to multiply that, I'm going to get 6, but the gallons go away. And this tells me that I am pumping 6 pounds of salt per minute into my container. Okay, now R out, it said it's getting pumped out at the same rate. So I know the brine solution is getting pumped out at 3 gallons per minute. And then this is the part that the book's just like, yeah, it's just this. And they don't explain it well. You guys might be able to grab it. But what we're doing here is this is the brine solution that's sitting inside of the container. It's already mixed up once it gets in there. And then this would be the mixed brine solution leaving. So what we have, remember that we're letting A, we set it up here. A is the amount of salt. So the leaving amount that we're going to have is going, I'm going to do one fraction here, would be the amount of salt, right? A pounds per, and then how many gallons are in the container? Well, 300. I don't know A. A is what I'm trying to find. A is the amount of salt that is coming out of the container. So if I multiply this, we get A over 100. Gallons cancel again. So I have, this should be pounds, I guess, per minute. So we have an inflow and an outflow. I think the book just says A over 100. That's what that is. The reason being is because we have 300 gallons in the tank. A is the amount of salt. So if I just divide them, that tells me how much is coming out, right? That's how much salt is actually in the container there. So now we create dA dt by just taking 6 and we minus A over 100, right? Notice this is not separable. Trying to think of a way. Is there a way? Yeah, this is actually separable. We could do that. Or we could use first order linear, whatever you prefer. I'm going to do first order linear. So we get dA dt plus 1/100th equals 6. Same thing, right? I just took the 100th out and then I added it over, right? I can find mu now. T not x. Mu t, and that's e to the 100th t, right? That was that integral. So this dE becomes d dt of our mu, e to the 1/100th t, times our output, which is A. Now remember, we got to multiply the other side also by mu. So don't forget that on this side. right? Remember, the whole point of this was now that I can integrate both sides, I'm going to get e to the 100th t times a. And then that side, if I integrate, okay, I think differentiation. So if I have an e to the 1/100th t, I know that's going to be there plus c. But I know when I take a derivative going backwards, it's going to introduce a hundredth. So I need to be able to cancel that hundred. So I'm going to put a 600 here because once that 1/100 comes out, 600 over 1/100 is just going to get me back to the 6. If that bothers you and you can't do it that way, do a u sub. All right, so we have our equation now, a of t. I just changed a with that in there. And I'm going to get 600 plus c e to the negative 100 t. They did give us an initial condition. Sorry, that was my dog barking. The initial condition is when 0 time, they told us in A, we have 50 pounds of salt that were dissolved in the 300 gallons. So we can use this, plug in. Usually works out because that e to the 0 is clean. So we get C to equal negative 550. So A of T is 600 minus 550 e to the negative 1/100th T. All right, so problem A, let's go ahead and answer both. I'm going to move this A0 because we're going to use that little area here in a moment. So I'm going to put it right there. So little a, we have our A of t. And we're going to say what happens to A of t as t goes to infinity. So here, we'll just write it out since we have A of t right above it. As t goes to infinity, A of t, right? Okay, well, if you look at that, since that negative, that would go to the bottom, and then e to the 1/100th t is just getting bigger, meaning that's going to go to 0. So it's going to go hunt to 600 pounds over time. If that was the same rate coming in, it's interesting that we could keep adding salt like that, and it never would go past the 600 pounds. All right, so we have A. Now B says, what if the solution is pumped out at a slower rate? So I'm going to put B over here because we're going to have to do a little bit of work. So B, guess we could highlight this. B says, what if our out was different? So what's going to change now is we'll do R in minus R out. I'm going to use a little R just to kind of help. R in, okay, now we're going to have 3 going in, but 2 gallons going out. So we're going to have 1 gallon per minute added to our tank, right? So after every minute, right? Because if I'm putting in 3 and only 2's coming out, I'm actually adding a gallon every minute. So after t minutes, there will be 300 plus t gallons of brine, right? Because we're adding 1 every minute because only 2 gallons are going out. Okay, so here's our actual our flow now. R out, the big R, is going to be A over 300 plus T times 2 now. That's the out. So it's not clean, but we're still going to use it. I got 2A over 300 plus T. Okay, and the in is the same. So the in didn't change. So now we have our dA dt minus, and then we're going to get 2 over 300 plus T. I left the A out because now it's going to go out here. And then that's equal to 6. So the only thing that changed was that rate. I just went back up here to this equation and just changed the A. That's the only thing that changed was that outflow. So now that is a first order linear. We could do mu. I'm going to let you guys do that because I feel like that you guys can handle first order linear. But how this works out here is I get a d dt, and it's going to turn out to be 300 plus t squared times a. And then we got to have that on the other side as well. So we get 6 times 300 plus t squared. And then you'd integrate, that's going to be a u sub. I guess I could do it. It's really not bad here. 300 plus t squared times a. This is just a U sub, so we're going to end up going up by 1, divide by 3. So I get 2, and it's going to be times 300 plus t to the third power plus c. All right, so that's a of t then. I can solve. I get 2 times 300 plus t plus c times 300 plus t negative 2. Right, that's how we got to that. I don't know if they gave us, I guess the initial condition would be the 0 with the 5, what was it, 330? Where was that at? My initial condition was right here. So if there was 50 in there, okay, I guess we could do this 50. Let me go ahead and add a page. Hold on one sec. Let me shrink this up. Move it up onto this page, add a page. And then go ahead and grab this. Thanks for your patience. Okay, there we go. So if now I'm plugging that in, okay, I get 50 equals 2 times 300 plus 0 plus c times 300 to the negative 2. I put 0 in for that. So we get 50 equals 600. And then this is going to be c over 300 squared. Not going to be pretty. I get a negative 550 equals c over 300 squared. And we're going to multiply. So c is, and I'm just going to leave it like that, 300 squared times negative 550. And then we could plug it in and be done. I'm going to go ahead and do that. So I'll go ahead and duplicate. This will be real easy for me. Move that over, delete the C, and go ahead and put C right there. And there we go. So we can put that there and be done. All right, so that's what it would be if it were to go out at a slower rate. Changes it actually pretty dramatically. All right, so there's our in and our outflow. The hardest part for that one, I believe, is just setting it up. So after this, we're gonna do one more video with one more application with electricity, some circuits.